7:55 p.m. on the 20th of April 2010, men aboard the Deepwater Horizon faced a choice. One instrument suggested the well was secure, another showed 1,400 pounds of pressure. Both could not be right. One answer meant stop, the other meant continue. They continued. The decision did not look like a disaster. There was no fire, no explosion. 94 minutes later, the rig was burning. 11 men would not make it home. The rig sank 2 days later. Oil flowed into the Gulf of Mexico for 87 days. But the disaster did not begin with the fire. It began when a warning became permission. The crucial question is not why the final safety system failed, it is why the crew ever needed it. The machine that took most of the blame sat almost a mile beneath the rig. It was the blowout preventer. A stack of hydraulic valves stood between the well and the ocean. Its final defence was a pair of powerful blades. They were supposed to cut the drill pipe and seal the well. They failed. But that failure came near the end. By then, hydrocarbons had already travelled thousands of feet upwards. The machine was trying to catch a disaster that had escaped every earlier defence. So what failed first? The Macondo well was being held shut by weight. The reservoir below contained oil and gas under enormous pressure. If the weight above became too light, the reservoir could push upwards. That weight came mainly from drilling mud. Despite the name, drilling mud is not simply dirty water. It is engineered to press down against the pressure below. As long as it remained heavy enough, the hydrocarbons stayed underground. But drilling had finished. The crew was preparing to leave the well temporarily. That required replacing heavy mud inside the riser with lighter seawater. The moment that happened, the force holding the reservoir down would weaken. The operation was safe only if another barrier had sealed the well. That barrier was cement, and nobody aboard the rig could see it. The cement sat more than 18,000 feet beneath sea level. If it held, the heavy mud could be removed safely. If it failed, oil and gas could enter the casing. The crew, therefore, had to test it indirectly. They reduced the pressure inside the well. Then they watched for flow or pressure returning. No flow meant the barrier was holding. Returning pressure meant something below was still pushing upwards. It was called a negative pressure test. The principle was simple. The result was not. And the first result should have stopped the operation. More fluid returned than expected. Pressure inside the drill pipe refused to remain at zero. The equipment was adjusted. The test was repeated. Again, the well behaved incorrectly. Approximately 15 barrels flowed back when fewer than 5 were expected. The pressure was reduced again. Then it rebuilt to 1,400 pounds per square inch. That meant energy was entering the system. But another line appeared to show no flow. The instruments contradicted one another. That was the decisive moment. The well could not be called secure until both readings made sense. Instead, the pressure was explained as a bladder effect. The theory suggested trapped fluid was creating a harmless reading. It offers a safe explanation for a dangerous result, but no clear procedure proved that explanation correct. The crew still had to choose which instrument to trust. They trusted the one that allowed work to continue. At 7:55 p.m, the test was declared successful. It had not shown that the well was safe. It had shown that the well was not understood. Then came the next revelation. The reassuring reading may have been the false one. Investigators later concluded that thick spacer fluid may have obstructed the line. It may have shown no flow because the route was blocked. The unexplained pressure remained. That alone should have stopped the operation. A safety test passes only when the whole system behaves as predicted. Macondo did not. But the job was already moving towards completion. The well had taken longer and cost more than planned. Mud still had to be transferred away. Tanks were being emptied and cleaned. The failed result became something to explain away. The well was opened. Heavy mud began to leave. Lighter seawater took its place. The weight holding the reservoir down began to disappear. Oil and gas entered the casing. At first, the warning was subtle. Then, the signals began agreeing. Flow increased when it should have decreased. Drill pipe pressure rose when it should have fallen. When the pump stopped, the well continued flowing. The warning was no longer one disputed gauge. The entire system was now saying the same thing. But other work was happening simultaneously. Mud was being pumped to a supply vessel. Monitoring tanks were being emptied or cleaned. Other fluid was being discharged overboard. These operations made the changing flow harder to recognise. The well was producing a signal. The work around it was producing noise. At approximately 9:20 p.m, the earlier test was still called good. Below the rig, the well was already out of control. But even then, chances remained. The clearest preventable point had come at 7:55. Stop the displacement. Restore the heavy mud. Investigate before continuing. But later warnings created further opportunities. At approximately 9:08, the pump stopped. The well continued flowing. By around 9:15, pressure had risen beyond 1,600 pounds per square inch. The well was still not shut in immediately. Every minute allowed the hydrocarbons to rise further. As gas moved upwards, it expanded. The flow accelerated. By the time the influx was recognised, hydrocarbons had travelled above the blowout preventer. Mud and seawater surged from the riser onto the rig. The flow was directed towards the mud-gas separator. That system could handle only limited amounts of gas. This was far beyond its capacity. Gas spread across the Deepwater Horizon. The crew was no longer interpreting a warning. They were trying to survive its consequences. Gas entered machinery spaces. The engines consumed it through their air intakes. The generators accelerated beyond their normal speed. At approximately 9:49 p.m, electrical power failed. The final emergency system was activated. Far below, the blowout preventer's shear rams moved towards the drill pipe. They were supposed to cut it and seal the well, but pressure had pushed the pipe away from the centre. Part of it now sat beyond the blade's effective cutting area. The rams closed. They damaged the pipe. They could not seal around it. Seconds later, the first explosion tore through the rig. A second followed. The final barrier had failed. But it had inherited a disaster already passed through every earlier defence. The cement failed to isolate the reservoir. The test produced contradictory results. The contradiction was not resolved. The dangerous reading was explained away. The test was declared successful. Heavy mud was replaced by lighter seawater. Other operations obscured the changing flow. Later warnings were not acted upon quickly enough. Hydrocarbons rose above the equipment designed to contain them. Gas overwhelmed the rig. The final barrier could not seal around an off-centre pipe. The blowout preventer became the most visible failure because it was the final one. But the last machine did not create the disaster. It inherited it. The explosion came at 9:49 p.m. The decisive failure came nearly 2 hours earlier. The gauge showed 1,400 pounds of unexplained pressure. That reading should have stopped the operation. Instead, it became an obstacle to explain away. The test was performed. It failed. Then, it was recorded as a success. The fire was the ending. The failure began earlier. That is the failure chain.